Hello. How you doing, Caitlin? Hello, everyone.
Hello.
I didn't realize I didn't have my video started. That was not helpful. Us old people shouldn't be allowed to use technology like this.
You're a physics professor. You should know how to use technology.
I do, but it changes all the time. Actually, the funny part is I signed in, like 30, 45 minutes early and sent y'all that email. And literally at like 9:56, my internet went out. The lights went out. My internet went out. Everything went out. I was like, oh, crap. So, yeah, I was discombobulated from the get-go. How's it going, Anthony? I see Anthony, Haley, Caitlin, Tristan, Josh is here. Sean's here. All sorts of cool stuff. So I apologize for being a couple minutes late. I had to reboot my Wi-Fi, all that good stuff. Did anybody have any questions before we get started?
No, but I did see that apparently TCC is opening up on June 10th.
Oh, that's good to know, right? Actually, I do have a class that starts July 7th too, so that makes it even worse. So July 7th, my other class starts, which is a Physics 202. And that's going to be real fun because it's a lab course and we literally have 2 labs a week. So I'm going to poop 2 labs a week until until we can get back into classroom, I reckon. In the fall, we've been informed that everything's going to be online again. The only thing that might not be online is labs. And even that could change. So we've decided to plan as if everything's going to be online, and we started making up stuff for next semester. So I don't know what else is going to happen. Hopefully we'll get some really good news and everything will start to die off and it'll magically disappear. And then we can go to regular teaching. That would be awesome.
So we might switch into regular classes.
No, we can't. Well, I'm not allowed to do that. But if the school opens up in time, which like June 10th, like he said, I can offer things like I can be there for office hours. I can offer some planetarium shows, all that kind of stuff. But far as I was told, we're not allowing any students the rest of the semester in the summer. But like I said, if they did do that, I would certainly get you guys together for a planetarium show or star show or something like that. So far, we haven't been given the go-ahead, though. How many of y'all were able to watch that Beyond the Big Bang other than, previous semesters? You were able to watch it, Caitlin? Did you have a service already, or did you have to buy it?
We have Cox cable here, so I was able to log in.
Cool. It's actually a very good movie. It literally covers the entire 2-semester sequence. It's got a few things it doesn't go in deep enough, like Newton's laws and that sort of thing. But it does cover virtually everything. It really does a good description of the history of the Big Bang, so that was nice. I just got permission from A&E that I can now record it and post it on Canvas and those learning management systems. So I'll be posting that for those of you who didn't get it. Does anyone have any questions about the process of the course or anything bothering them about the syllabus? I think there's a typo on there. I've got 2 different discrepancies about which day you guys are supposed to log in. I'll be honest with you, if you're logging in like 3 different days a week, I'm not going to count that ever as an absent. So just make sure you do 3 separate days a week, and no matter what my syllabus says, you'll be fine.
Are you planning on uploading a practice test for us?
You caught me off guard. I was completely certain that I'd already done that. So yes, that will definitely be done. And what I'll probably do is extend your test due date until like Wednesday or Thursday.
Okay, cool.
Okay.
When are the reflection questions and stuff due?
The ideal scenario, as soon as you can answer them, you should answer them, like within a day or so, and then turn them in immediately thereafter. But there's the due date's basically the due date for all the astro points.
So the reflection questions, are they considered like some of the homework assignments, so they're not extra points?
No, they're definitely extra points.
Okay.
Just if you talk to a person with a PhD in education, they'll tell you that kind of learning is like super strong. So if you review your notes or the text material within 24 to 48 hours, which is what reflection questions make you do, then you tend to do a whole letter grade higher. So that's why I make them available.
Okay. Okay.
But yeah, they're just astro points. The only things that technically really required are taking the tests, and you have to do a certain number of those homeworks, and you got to get a certain number of astro points total. I think it's 1,500 is what I said this semester as well.
Okay. On the Big Bang reflection questions, there were two at the end that said that you would explain those. Is that something we're gonna do?
Yeah, that was explained on the video that I posted on, I think it was Monday. So if you watch that, I talk at the beginning about the Big Bang. Basically, it's just, and I can give you a rough estimate of what it is about anyways, if I remember correctly, because it's been a while since I looked exactly at these questions. You don't have them in front of you, do you, before I answer the entirely wrong question?
Yeah. 1 minute. Let me get out of full screen. And maybe I just missed the video posting. You posted it for this week's stuff, right?
Yeah, actually it was, because your class included part of chapter 2, it was actually in last week's stuff.
Okay, so it was part of the self-addressed envelope and then the explanation.
Yeah, right below that is a discussion of intro to the celestial sphere, but I opened up with an intro to the beyond the Big Bang, or excuse me, intro to Big Bang as well. Let me give you that spiel though. I like to talk about it anyways. It's kind of an interesting thing, and it's a lot of times in astronomy, people get the idea that science and religion are bumping heads, and I'm not one of those people that believe that necessarily. I'm one of those non-overlapping magisteria philosophy, like Stephen Jay Gould said. So there's this really neat story in that basically the Big Bang created the universe. And in order for you to really understand that, you have to know what the universe is. The universe is not all the matter and energy in existence. It's actually, oh, thank you, I got you. Thanks, Caitlin. And I saw Haley did get it from the YouTube link. I'm glad that YouTube link's still working. So the universe is not just all the matter and energy in space. The universe is the space itself. So this is the weirdest thing, but the universe was created in the Big Bang. We don't know what started that Big Bang. And that one of the opening sentences of Beyond the Big Bang, you really need to read the transcripts to make sense of what Brian Greene's saying. But he's saying, and we still don't know what that is until today. That's like a parenthetical is where he says, and we still don't know what that is until today. What he's saying is, we're going to look at it from the Big Bang until today. And then inside of that, he said, by the way, we don't know what started the Big Bang. So don't think that we now know what started the Big Bang. That first sentence bothered me. It was a typical difference between a written word and spoken word. So the Big Bang created the universe, which included all the space and all the matter. But the problem is when you actually look at how the Big Bang could have occurred, it can only produce hydrogen and helium in any large amounts. We might, and some people have argued that you definitely get lithium and beryllium and maybe even cobalt, but or not cobalt, excuse me, boron. So other than that, there's nothing. In other words, the Big Bang just created the space, which is weird because the space, it's not like this, giant emptiness before the Big Bang, and then this one little location in that giant emptiness explodes and matter comes out. That's not it at all. In fact, if it doesn't hurt your head to think about what the Big Bang is, you're probably not thinking about it enough. But it's this infinitesimal point that we don't necessarily think is inside anything. We don't even know if it's inside something bigger. But in that infinitesimal point, space blows up. And this is the envelope of space, if you will. That's getting larger and larger. And when that happened, basically only hydrogen and helium came out in trace amounts of those other elements, lithium, beryllium, that sort of thing. But if we're claiming that created the universe and all the matter in it, and we look at a periodic table, we see that there's like, you know, well over 100 elements existing. So it leaves you with a lot of explaining to do. Well, it turns out the nucleosynthesis that's talked about in the Big Bang shows us where those other elements come from. Basically, when a high mass star runs out of hydrogen in its core, so it's got all these layers of plasma outside of the core, and then inside the core, which may be 10-20% of the radius, is the only area where the temperature is at least 10 million Kelvin. And that 10 million Kelvin is what's required to make the atoms, which at this point, because it's so hot, they're basically just nuclei, to make the nuclei go fast enough where two protons can run into each other. Because remember, it's just hydrogen and helium, right? So you're basically having a bunch of hydrogen atoms broken up into just a nuclei, which are protons, and protons are like charged. They're both positive, and they want to get away from each other. If you throw them at each other fast enough, they can overcome that large force holding them apart, and then the strong nuclear force will grab them. But the strong nuclear force is super strong, but it only reaches out slightly, so it's like Velcro. So if you get it going 10 million Kelvin, then those protons can suck up to each other. And in fact, one of them will spontaneously turn into a neutron. Conservation of charge dictates that it's got to spit out a positron, which is the antiparticle of electron. And conservation of energy and momentum and all that good stuff tells us that a neutrino would come out as well. That then gives you a proton and a neutron, which is just basically a heavy form of hydrogen. But two of those things will run into each other, and you end up getting a proton and two protons and a neutron, which is actually helium. It's just not the helium isotope that's very stable. So we'll get another collision later, and that'll make an alpha particle, which is a helium nucleus. When you run out of that hydrogen in the core, remember the core is that 10 to 20% of the radius area where the temperature is at 10 million Kelvin. And at that 10 million Kelvin, that's the only place where you have high enough speeds where hydrogen can bombard into hydrogen. But with the larger mass stars, our models show that there's no circulation going from the inner part, the core, to the outer parts. So whatever amount of hydrogen you have in that core, that's all you get. So when you are burning hydrogen and producing helium, basically what's building up is nothing but helium in the core. However, when you start running out of hydrogen, the reactions slow down. Because the reactions slow down, the radiation that they were putting out, the reactions were putting out, becomes a lower pressure. So the gravity outside squishes it. When it squishes it, that causes it to heat up a little bit more. And if there's enough mass above it, that 10 million Kelvin is greatly exceeded and reaches the next critical barrier, which is around 100 million Kelvin. And at 100 million Kelvin, you can actually fuse helium into carbon. Some other things come out of it, but you definitely get helium as well. I mean, you definitely get carbon as well. So when that happens, when it squeezes down like that, we now get up to an even higher temperature, and we can start fusing helium into carbon. And of course, you'll run out of helium again as well. So that's going to happen again later. If it's got enough mass, it'll compress again to reach the next critical temperature. And then you'll start fusing carbon into other things. All the other reactions can still take place as well, but you'll start getting more and more elements. And in fact, you go like every other element on the periodic table is created along that path where you're running out of fuel. And then outside of that envelope, there's a little shell burning the last thing you were burning. And outside that is this shell burning the thing before last that you were burning, and all this neat stuff. So you see that slowly inside a really big massive star, you can generate all the elements. But the problem is you don't get actually all the elements. Like I said, you only get roughly every other one. And in fact, once you get to something fusing into iron, there's no fusion or fission that gives off more energy than it takes to make it happen. So iron's the dead end. So what happens is at the very end, you get an iron core. Everything else is basically fused away. There's no radiation pressure anymore because there's no more reactions going on. So gravity crushes it. And we don't actually understand all the details of how gravity crushes it or how the explosion occurs, but we think neutrinos are involved. and it crushes it, and there's a large explosion called a supernova explosion that blows not only all those shells of all those materials that were just created, which, like I said, was about every other element up to iron. It releases all those into nearby space. But in addition to that, that energy is so huge that it actually provides temperatures where other fusions can take place. And we, in fact, can account for every element that we find on Earth and every element we found in space, basically, from that nuclear explosion. The neat thing is, you notice you didn't get gold, you didn't get silver, you didn't get platinum. So all the gold, the silver, the platinum that you have in your, necklaces, earrings, jewelry, teeth, or whatever, that stuff being, sort of rare is kind of expensive. And the reason that it's sort of rare and expensive is that it was created in a supernova explosion. Now, when that explosion occurred, that not only sent all those elements out and about, but it basically we find stars developing galaxies. In fact, we think galaxies sort of started creation before the stars did. And then those galaxies can distribute that matter all throughout space. So you have several little nebulous clouds that can become planetary systems. So that grants us all the elements that we need for life and the world as we know it to exist. The problem is those stars, those high mass stars that create all those elements, only live on the order of 10 million to 100 million years. And that's a long time for us, but it's not very long for evolution and origin of life to take place. So this is what I mean by it's like we've just been given every little thing that we possibly need. That's one way of looking at it. And the little thing that we possibly need to get life to be where it is now we need low mass stars, because low mass stars can take those elements from, second and third generation stars, take those elements that have been created, the iron that's in our blood, for instance, the carbon that's part of our bodies, the oxygen that's part of our bodies. It can take all those elements and we can have an origin of life, which isn't completely worked out, but we've done some experiments that create some pretty impressive things. The UREY experiment, UREY experiment, is a case in point. But basically, if you subject the elements that were present in the early Earth to lightning and pressure and stuff like you'd have in the atmosphere of the early Earth, we've actually had basically certain elements and proteins and compounds created that are the predecessors to life. So that's sort of the big deal, and that's as close as we've come to understanding or explaining I shouldn't say understanding, to explaining the origins of life. Now, in addition to that, because these stars like ours is one solar mass star, it basically will live for about 10 billion years. So that 10 billion years gives you enough time to go from that origin of life, which is some self-replicating molecule, to something more complex, which is like a cell, to cells that replicate, to prokaryote and karyote cells, and then to actually life, given the random processes of mutations, along with the completely non-random process of selection. So that process takes a long, long time, and you can only get it when you have billions of years to work with. So it's kind of awesome. We can see a Big Bang creates, 2 elements mainly, but maybe 4 or 5 total. High mass stars create all the other elements, and then low mass stars have to exist to actually allow life to grow and come into being. And then finally, you also have to have galaxies, which we do have, to spread that new matter, that new those new elements around, so that life can come to fruition. So I think that sort of explains what those questions are. It says the following came from your instructor's explanation of the video. If the Big Bang only created hydrogen, helium, and a little lithium, where did the other elements come from? Y'all think y'all can answer that one now, right? Mr. Younger's long-winded, so it's pretty easy, right? Explain in some detail. And 7, the following came from your instructor. Why are low mass stars necessary to explain our universe? I think y'all can get that now too. So yeah, absolutely. If y'all missed that video from last week, I sent an email to remind everybody it was there, but I suspect because I put it in week 1 that made for some confusion. So I'm sure it's my fault. That'll help you. But I am going to take the test. I need to make myself a note. I am going to make the test due Thursday instead of Monday because I didn't put up the practice test. Okay, so if you still have some attempts left, you still got more time to do that. I'll put up the practice test right after I get off of here, and that'll help you guys with that.
And so what's the video called in which you explain that?
It's called, the video I posted, I think I called it the Introduction to the Celestial Sphere.
Okay.
It should be in week 1's module. Week
Oh, I
1
see it.
module, of course, also had the self-addressed envelope and the first explanation. I actually got 4 more videos for explaining that video, but I haven't posted those yet. They'll
Okay.
come up later. They're more math stuff that people didn't care about, so I thought it was more important to get the other stuff up.
Are you planning on uploading each one of these lectures online?
Yeah, I'll upload all of them on Canvas. I'm actually putting them on my YouTube channel, the ones that I'm allowed to. I'll put them on my YouTube channel, and then I make a link to that to our Canvas course, and then
Okay.
you guys see it that way.
Great.
I have a question about the Smart Work 5
Mhm.
stuff. So on Canvas, it says there's 2 of them for chapter 2, and on the grading, it doesn't show one of them complete. And every time I try to click on it to open it up, it doesn't.
Oh, gotcha.
The link
Yeah.
to go onto it.
Yeah, okay, that's a problem with my grade book. It automatically copies assignments from previous semesters, but when I open up Smart Work and create my course for the new semester, it leaves all the old ones and then creates new ones.
Okay.
So you're only supposed to get 1 of those per chapter, so don't fret that. Now with
Okay.
reflection questions, sometimes I'll do 4 or 5, but again, theirs aren't necessarily required. But yeah, that happens. The grade book will have like a bunch of assignments that are on there. The thing that matters is, one, you look at the category and see what it's worth. If the category is worth 0, then you know it's not too big of a deal, except for the case like astro points are worth nothing, but you know you have to have 1,500 of them minimum to maintain your test average as the course grade.
Okay.
You have to open up the SmartWorks through the modules. You can't open it up through the grade book.
Yeah, okay, good idea. I didn't know that's the way students are doing
Yeah.
it. Yeah, so don't go to the grade book. Definitely go through the module. It'll lead you to confusion otherwise.
No,
I wouldn't
that.
access
I got the
anything
link
except
for the website too, so I could just go through the website too, but it wouldn't show it, so that's why I was a little bit worried. But
Yeah, gotcha. Yeah, try not to do it through the website either, just because that sometimes causes some problems with Norton's ability to transfer grades to our grade book.
Okay.
So I've had students, sometimes I'll send them a snotty letter and say, "Hey, you didn't do any of your homework. What are you doing?" And then they were, of course, flipping out because they had done all their homeworks and couldn't find out they just hadn't ported to Canvas.
All right.
All right. Any other questions about the course or anything?
And are you going to upload the chapter 1, chapter 2 tests?
That's not up yet either?
No.
God dang it. Okay, so yeah, it looks like I'm going to push chapter 2, definitely going to push chapter 1 and 2 tests back to Thursday, like I already said. So yeah, I will post that immediately after getting offline.
Okay.
Thanks
you.
for letting me know, Anthony. It's funny part is it's a whole section, and the whole section hasn't been opened evidently, because there's a section called practice tests, and I think there's a section called tests, a module for each of those. I think that's where I'm going to put everything this semester instead of hiding them in individual weeks, because when a student misses a test, it makes them really, really hard for them to find out where it was unless they remember exactly what week we had it.
So does that mean that chapter 3 and 4 tests will be next week, or will that get pushed a week?
They're going to be stacked up a little bit. Probably what I'll do is 3 and 4 I think are supposed to be due next week, period. So maybe instead of Monday, the week after, it'll be due maybe Wednesday, and I'll sort of trickle them back that way. But it's going to be very common, since we're doing 10 weeks, it's very common for you to have 2 tests possible to be taken on the same week.
Okay.
Okay.
So does
If you
that
keep-
mean that
ahead.
chapter 4 will be posted soon? Because we only have chapter 3 right now.
Yes, yeah. In fact, that's one of the things. Well, I'm covering up through chapter 3 right now. Chapter 4 will be posted immediately. Next week, the assignment will be basically, hey, take test 2, which is on chapters 3 and 4, but you'll have until the following Monday. And I should have chapter 3 is already available, but chapter 4 will be available today. Okay. Anything else?
When we get to the little pinwheel of what are they? Not the constellations. Like Aquarius, Gemini, Leo, and
Oh,
all
yeah.
that. Can you re-explain that before the test?
Yeah, I'm actually getting ready to do that right now. That's one of the lecture topics I'm getting ready to cover to make sure and I'm going to record it in real time. You guys are not required to be here, so you're welcome to leave. But if you don't mind, it's perfectly cool for you to hang out here. Or like I said, you can split. Yeah, did Kadra try to say something? I saw her come in a little bit late. Kadra, can you speak?
Yeah, she asked when are the chapter outline reflection questions due?
Okay, gotcha. So all the reflection questions, I allow them till basically the last day for Astro Points or whatever the syllabus said on that. But it's best for you to do them within 24 to 48 hours of learning the material that's in them. So what I would do is before you even start reading chapter 2, read the chapter 2 reflection questions. Same thing with chapter 3. So you'll have some idea what you're looking for. And then while you're reading, if you can get the information, okay, well, I should probably make sure I do this within the next 24 hours to 48 hours. That's the statistically helpful educational tip. So that's the whole purpose of the reflection questions, but I gave you points to encourage you to do them. But at the end of the day, I'm going to give you the points, whether you do them the way to help you or just the way to get you to points. All right. Well, since it looks like I got everybody's questions, I'm going to share my screen with you and talk about some stuff that we hadn't done in chapter 2, as well as some stuff that I might even go into chapter 3. Let's put it that way. Again, this is an online class, so I'm not necessarily going to be able to lecture every bit of material, but I'm trying to. But it's just there's a lot of stuff to do. So anyways, I'm always here to answer questions, and each week we're definitely going to have at least one meeting. I'm trying to see if I can schedule a second meeting every week. If I can do that, again, that will be an optional one, but it'll be more time for you to interact with me. I might even do it in such a way that I'm teaching another class somewhere else because there was some uncertainty as to whether I'd have a job this summer because of the plague that we're going through. So anyways, I took another job over at another school just as an adjunct, just to make sure I could, make my bills and that sort of thing. And I might be able to do all of both the classes at the same time, because I get a very low turnout either way. And that class is even smaller, like 6 students. So anyways, I'm going to go ahead and share the screen on chapter 2 and do some of the things that we didn't already cover. I might even start over from sort of the beginning of those slides so you can make sense of the video that I already showed, since it seems like some people might not have watched it anyways.
Hey, Mr. Younger.
Yes, ma'am.
We had a question. I don't want to say her name because I don't want to butcher it, but
Roshana or whatever her name was?
Yeah.
Yes. It was when it asked celestial sphere. Oh, okay. So those questions that got those colons and double colons, those are called analog questions. So, or analogy questions. So what it's supposed to be read is the celestial sphere is to the Earth as blank is to something like that. So the celestial sphere is to the Earth as maybe longitude and latitude is to, celestial sphere is to Earth as maybe, let's say celestial.
Well, I figured it was that, but then you asked for a coordinate, and I'm like, wait, what? I didn't understand it.
Yeah, have you watched the video that I posted? I put it in week 2, and you might have been one of the people that missed it. I explained basically the celestial sphere and and I'm actually getting ready to go over it again now, so it might help you. You want to just wait and see if that helps you, and then you can ask during or even after.
Okay.
Okay. All right, we'll do that. And like I said, guys, if you have any questions, this is just like a regular class. All you got to do is just speak up. I don't care about raising your hand or anything. Just try not to talk over anybody else. But let me go ahead and share this. It looks like here. And I was going to jump to this slide, but in light of people not seeing the video, I think I'm going to jump to this slide. So, okay, so they opened up with what is a solar eclipse. We'll get to that later. That's the later part of the chapter. If you go out in the night sky, you'll find that, in fact, there's this neat little area where it looks like everything is rotating around it. See that little spot right there? And in fact, that one little star that's going around, that is actually moving, but it's hard for us to tell with the naked eye. That star is Polaris. And notice how low it is in the sky here and how high it is in the sky here. So when it's high in the sky, that means you're further north, and when it's low in the sky, that means you're further south. This is actually taken at the Arches National Park in Utah. But if you did a time, opened your aperture on your camera for, you know, on the order of, it looks like in this case, maybe they did 4 hours. One looks way brighter than it did when you were there, but two, you get these streaks. Of course, those streaks are hard to tell whether it's going, it's clearly rotating, but it's hard to tell whether it's going in the clockwise or counterclockwise direction. I'm going to convince you guys that it goes in the there you go, in the counterclockwise direction. So let's look. So first off, we didn't talk about this in the video at all, but it turns out all the ancient cultures, when they became cultures and left writing, were already studying astronomy. And in fact, before they even had the ability to write, like in the case of Stonehenge and stuff like that, they didn't have the ability to write yet, and they were already building things related to astronomy. This, in fact, there's, you know, a heel stone. If you line the heel stone up with a certain stone, it shows where the sun rises at the farthest north. And then another one shows where the sun rises at the farthest south. Another one shows where the moon rises at the farthest north, and where the moon sets at the farthest, or excuse me, rises at the farthest south. All sorts of cool stuff like that. It's really amazing how much they figured out. And, you know, it's sort of necessary, because if you're going to become a culture that isn't, you know, hunters and gatherers, you have to build on agriculture. You have to actually have a food supply that can allow you to survive through the winter months. And in order for you to do that, you have to know when the winter months come. And in order for you to get that, the best clock and calendar we have is our sky. You know, we can use the height of the sun to tell us what time of day it is. We can use the height of the moon to tell us what time of the night it is. We can use the Big Dipper to tell what time of the night it is as well. But we can also use the stars in certain alignments where the sun rises and tell us what days of the year it is, basically. So that's what they were doing. This is that celestial sphere we talked about. So if you look at the Earth down here, the Earth would have an equator right along here. It would have a prime meridian going through Greenwich, England. And then it would have a bunch of other meridians and a bunch of other lines of latitude. The latitude, remember, are like this. So they're parallel, like rungs of a ladder. The lines of longitude are from vertical, are from the North Pole to the South Pole. So that's our coordinate system on Earth. So when we started studying astronomy, it would be natural to use a similar, coordinate system for the actual celestial sphere. So just like we saw earlier in those photos, it does appear that there's one spot in the sky, i.e. this spot right here, the North Celestial Pole, that doesn't fall. So if you imagine all the stars being painted on the inside of a giant sphere centered on us, that's a perfect representation of the stars. So they made the celestial sphere, and basically if you imagine the Earth being plexiglass, there being a light bulb in the center, the equator's shadow would make the celestial equator. And that's what that orange line right there is. And in fact, the North Pole the shadow of the North Pole would make the North Celestial Pole. The shadow of the South Pole would make the South Celestial Pole. And then we just need to find something equivalent to the prime meridian. So the prime meridian, like I said, we chose it to go through Greenwich, England, because Great Britain happened to be the superpower at the time. So, you know, if it was today, if it was 10 years ago, it might have been us. If it was today, I don't know if it's going to be China or what. Somebody's kicking our butt. It's not helping. So anyways, what we did for the celestial ones is a little bit different, though. We don't have, you know, this powerful constellation in the sky that we know all this cool stuff about, that has, you know, Barry White and all these cool singers and stuff. So we just go for whatever, right? Well, what we find out is that over time, if you watch the sun appears to be orbiting us. So it doesn't, you know, like the stars, they stay like they're glued to the inside of the sphere. And, you know, the shape of, for instance, the constellation Ursa Major always looks the same. Stars and those planetos, which means wanderers, wander through, planets and those suns and stuff like that, they actually wander through our celestial sphere. And when the sun does it, it seems to roughly set basically no shadow at noon on the vernal equinox if you happen to be on the equator. So that means it's lined up with the center of the Earth, the equator, and the equator on that particular time at that particular day. That's the vernal equinox, is roughly 321. If you go to the Tropic of Cancer, which I'm 95% sure is the northern one, it turns out that the sun will cast no shadow on that day either if you happen to be on the Tropic of Cancer. Okay. And then, and that's 621 roughly, that's the summer solstice. And then if you happen to be on the equator again on 921 at noon, the sun will cast no shadow. And what I mean by casting no shadow is basically a vertical pole. The sun's going to be hitting directly from above it, so it's vertical, so it can't have a shadow unless it was like an umbrella. An umbrella would make a shadow, but a pole wouldn't make a shadow. Umbrella would make a shadow because the top is bigger than the bottom, so the whole bottom would be the shadow, or the whole outer circumference would make the shadow rim. And then if you waited until 1221, you would find that at noon, the sun casts no shadow on the Tropic of Capricorn. Okay, so that let us figure out that the sun sort of follows this path. It goes from below the celestial equator, hits it on 321, reaches its highest point away from it on 621, the summer solstice, crosses it again on 921, and that's called the autumnal equinox, and then gets as furthest below it on 1221, called the winter solstice, and then it starts back over again. Okay, so that's the path the sun follows. So what we chose to do is the day of the vernal equinox, or the location in the sky that the vernal equinox occurs, is our quote-unquote prime meridian. So that blue line right there is like our prime meridian for the celestial sphere. So if one of those analog questions asks you, Roshana, how is the, or let's say the prime meridian is to Earth as blank is to the celestial sphere, then you'd say vernal equinox. Does that make sense? So that's the kind of thing. And that's there's two coordinates, just like we have latitude north, you know, if you go above the equator 5 degrees, then that's 5 degrees north latitude. If you go below the equator south, then that's, and you go 5 degrees, say that's south 5 degrees latitude. Well, you also have a coordinate for longitude. If you go to the west of the Greenwich line, or the prime meridian, let's say you go 70 degrees, then you'll be at 70 degrees west longitude. If you go to the east, 15 degrees, you'll be 15 degrees east longitude. So what we did is we made instead of a latitude system, we made a declination system. And just like on Earth, the 0 is the equator. So if I go up 23.5 degrees, which is what this line is, that's why it just skirts across the ecliptic there. The path that the sun follows is called the ecliptic. If I go up 23.5 degrees, it doesn't make any sense to talk about north and south. So we just call it positive 23.5 degrees declination. So that's positive 23.5 degrees. This would be negative 23.5 degrees. This should be more or less like directly over. Well, I don't want to say that. No, it's directly over. If you shot a light from the center of the Earth through the Tropic of Cancer, it would hit the positive 23.5 degrees declination, and the Tropic of Capricorn would be hitting the negative 23.5 degrees. Now the prime meridian becomes the 0 of what we call right ascension, R-I-G-H-T, ascension. And you know, ascend means go up. So what that means is if you look outside the celestial sphere, like we're God or something, you can't be looking at it from the Earth there, you'll get left ascension. But if we look at it from out here, this line right here would be, and check this out, they use hours and minutes and seconds instead of degrees, but this would be 0 hours right ascension. If we divide basically 360 degrees by 24, we get 15. So if we go 15 degrees to the right, I'm now at 1 hour right ascension, and then 2 hours right ascension at 30 degrees, 3 hours right ascension, 4 hours right ascension, 5 hours, 6 hours, and so on and so forth. And once you get all the way back, it's 24 hours right ascension, which is the same as 0. Okay, so that's the coordinate system that we use. Right ascension, which is measured in hours, minutes, and seconds. So like if you divide a degree by 60, that'll be 60 minutes of arc. And if you divide a minute of arc by 60, that'll be 60 degrees, or excuse me, seconds of arc. So that's our celestial sphere. Let me show you another picture that'll help you with this, though. We know, for instance, when we look at the Earth, let me look back here, you can sort of see, this is supposed to be the Yucatan Peninsula. This is South America. Florida be right here. Well, you know that we get to see the sun before California does. So it's clear that the Earth is, in fact, rotating this way. Everybody see that? That it's rotating from left to right like this? So in our celestial sphere model, we can't really sense that the Earth is moving. So instead, we pretend the celestial sphere is rotating this way to the left instead. Celestial sphere is moving to the left like this. Okay, so that's how we use it to predict how stars move and stuff like that. There's naming all the parts. The ecliptic, the ancients realized that when the moon was on that special line that they had discovered in the sky, that they were likely to have an eclipse, so they named it the ecliptic. We now know that it's actually the orbit of the Earth, sort of traced as if the sun were moving onto the celestial sphere. Directly overhead, by the way, is called your zenith, and directly below your feet is called your nadir, N-A-D-I-R. So you can see that in the words there. Now, in terms of this, let's imagine instead of this dude who's being on the North Pole, right? This guy right here is over here on the North Pole. Let me show you something else to give you an idea how the actual stars appear to move. You can see it from that diagram there. But what I'm going to do is turn to my document cam. Okay. So hopefully this will be somewhat in focus. I think I can get it a little better than that, though. There you go. So what we have is the Earth, and I'm going to draw it kind of small for a reason, and evidently kind of dumpy. So here's California, Baja. There's the Yucatan Peninsula. There's Florida. There's the East Coast. I made it really small on purpose, okay? The equator is going roughly around here. We know that the Earth is technically rotating this way. So now it looks like Mike Wazowski. But instead, we're going to pretend that there's a celestial sphere that is rotating, or excuse me, that is rotating this way. Okay? That's what we're going to pretend. So if we consider someone at the surface of the Earth on somewhere other than the North Pole, then I have to draw the Earth tilted for us, the human beings, to be vertical. So if a human stands right here, obviously way out of scale, this line pointing from the center of the Earth up through their bum points to their line of latitude, and in fact is vertical. So this is their zenith up here. And this down here would be their nadir. Let me get this paper right. This down here would be their nadir. Now we're going to imagine as if they're on a celestial sphere, or under a celestial sphere, if you will. And we know that the celestial sphere's equator is right over top of the Earth's equator, so that's the celestial sphere's equator. We also know that if you draw a line through the axis of rotation of the Earth, you'll run into the North Celestial Pole, and this, of course, would be the South Celestial Pole. Okay? Now, the celestial sphere is huge. Like the nearest star to us is 4.2 light years away. So compared to a light year, the radius of the Earth is infinitesimal. So really, this person is standing right here. That means their horizon is right here. And if I went straight that way, staying on the paper, this would be what's called the north point. That's the point on the horizon that's due north of you. And this, of course, would be the south point. And if we go into the page, that way on the back side, we see the east point, and we go out of the page, up here would be the west point. So that's where, if you've seen malls and, of course, schools called North Point, South Point, East Point, West Point, that's what they're sort of referring to as those old navigational terms. Now, the cool thing with this is if I imagine this person reaching his arm out over here and putting his hand on the inside of the celestial sphere, Remember that celestial sphere is rotating this way. Remember how I drew it this way? It's rotating this way, which on Earth, if we're saying we're roughly in North Carolina or Virginia, right? We're right there. So that means the celestial sphere is rotating this way. And it's a big rigid sphere, so one part moves the same direction that all the other parts move. So when he puts his arm out there, you can see his arm is actually going to spin out of the page, then go back into the page, and then go back behind the page and come back like that. Now, if you turn yourself and look, you'd see that's clearly a counterclockwise rotation. In other words, him looking at his hand would see that the celestial sphere is rotating counterclockwise about the center point right here, which I said is Polaris. Okay? So that's why we get that image that we saw earlier with the stars all going around one central star in a counterclockwise direction. That's how we know that they're going counterclockwise. If I was in the southern hemisphere, though, I could actually find a spot where it looked like the center, but everything would be rotating clockwise. And that's what would happen if he stuck his arm way down here. His arm would appear to go into the page, back behind the page, then come back out like this. And if you look at if you look that way, you see, oh wow, it's going clockwise in the southern side. Okay. So when I do that, I can make some really grandiose conclusions. And one of them is this. There's the path that the sun actually follows. See, this is up here. I label the declination. So positive 23.5 degrees, negative 23.5 degrees. But I also label the dates. This is 321, 621, 921, 1221, and then back to 321. And here I also label the right ascensions. So 0 hours, 6 hours, 12 hours, 18 hours, 24 hours. And then that allows me to ask you questions like, what's the right ascension and declination of the sun on 621? And you'd say, oh, well, 621, it has a declination of positive 23.5 and a right ascension of 6 hours. Or if I ask you 925, it's going to be, or 921, it's going to be 0 declination and 12 hours right ascension. If I ask you 1221, it'll be 18 hours right ascension and negative 23.5 declination. So that's something we can use. Something else we can now see as well. If I try to draw that circle that I just showed you with the guy's hand that he was holding near the North Pole or near Polaris, this is the circle you get. Okay, so if I make the horizon and I put north right here, east on this side, and west on this side, what I'd see is a bunch of counterclockwise circles centered on roughly Polaris. It's so close we might as well consider it Polaris. And you'll see a bunch of counterclockwise circles, but since it's rigid, you got to keep drawing that no matter how far out you go. So that gives me an answer to like 6 different questions right off the get-go. If I see a star at 8 p.m. directly east of us, and I come back at 9 p.m., I might ask you in which direction or directions will it have moved? And I'd give you these choices: up, down, left, right, up and to the left, up and to the right, down and to the left, down and to the right, or not at all. You can see it went from this spot on the green line to evidently this spot on the green line. So evidently it went up and to the right. So that's how you answer questions like that. If I said one was in the west at 8 p.m. and I asked which direction will it have moved by 9 p.m., notice it's going to go from this spot on the green line to this spot on the green line, say. And you don't have to know how far that is. That's not the relevant point. Its main thing is you know it's going to the right and down. So the right answer for that one's down and to the right. If I say a star is to the right of Polaris at 8 p.m., remember it takes about 24 hours to go all the way around here. So each quarter would take how long? If it takes 24 hours to go from here to here, how long would it take to go from here to here? Anyone? I think Edwin knows, but his speaker's off. It's about 6 hours, right? So as long as I ask you a question less than 6 hours, you know it's going to go from this spot to somewhere on the green line between here, and you see that direction is up and to the left. I can also ask you, hey, there's a star above Polaris. In which direction will it have moved an hour later? And you say down and to the left. If it's to the right of Polaris, it'll have moved down and to the right. If it's to the below Polaris, it'll move up and to the right. So there's 6 different questions I can ask you, and actually there's an infinity of them, because I could ask it for 8 p.m. to 9 p.m. I could ask it for 8 p.m. to 8:30. I could ask it for 9 to 10, 9:30 to 10, 9 to 9:30, all those different questions. But there's basically 6 that are different. Now remember what I told you, when he put his hand above the on the sphere in the south, he got a clockwise circle, and the center was down below the horizon. So I draw south here, east on the left, and west on the right. And we all know things rise in the east half and set in the western half. So that's what I'm showing here, is the star rising, reaching its highest point, and then setting. So what you see is actually stars tend to get their highest in the sky when they're due south, or directly overhead, obviously. But if I ask you, hey, I see a star due south of me at 8 p.m., in which direction or directions will it have moved? You say, well, it's going to go from this green spot to one of these green spots, so it's down and to the right. So there's 7 questions total we got just from knowing that. That's kind of cool, and that's what we get from the celestial sphere. We can go further with the celestial sphere and work out some math, and I did that in the video. I definitely recommend you check that video out. But let me now turn back to the screen that I was on. So now you can see how they got this circle here. All I had to do is just imagine me standing right here, and then what that tilted Earth and tilted celestial sphere calls, and it calls us to rotate or see rotation. The stars, by the way, that are in between the North Pole and the Equator, and your horizon, are called circumpolar stars, and back in ancient Greece they were called the imperishables because they never set. So the ancient Greeks and the ancient Egyptians even knew that they never set.
I have a question.
Yes, go for it.
It's not exactly relevant to this, but I don't want to potentially forget it. So
Yeah.
when it comes to the 3 attempts, I think it was for the tests, do you take the highest grading one?
Absolutely, every time.
Okay, gotcha.
Yep. The only time you don't get multiple ones is the final.
Okay.
All right. So if you actually were at the North Pole, or at the Equator, you can see that the North Celestial Sphere is still rotating that same direction, which is, like I said, it looks like counterclockwise when we look at it. But the people on the North Pole, they actually just see stars moving to the left, basically. And people at the Equator, they're going to see stars rise, go straight up, and then set straight down. So that's kind of crazy, unless they look north and south. Of course, if they're looking east and west, they're going to see them go up and down. If they look to the north, they're going to see them going counterclockwise. If they look to the south, they're going to see them going clockwise. I usually don't ask questions about the other latitudes, but I definitely ask questions about our latitudes. You'll see those on the practice test, which for some reason I didn't make available to you yet. Here's the one for 30 degrees, which is more like us. So when you look at that, you can see, hey, if he reached his hand out, obviously his hand would go in that direction. And from his perspective, not from the way we're looking at it, remember he's down here. From his perspective, he'd see him moving to the in a counterclockwise circle. And if you look back here, he'd see these moving in a clockwise circle. Does that make sense to you all? So that's how we got all that stuff. There's actually some math that you can get from the flat diagram of the one I just drew, where you can determine that the height of the celestial equator in the sky is 90 degrees minus your latitude. So if your latitude's 30, you go 90 minus 30, and that's 60. So that would be 60 degrees above your south point is where the celestial equator is. And the actual north celestial pole, which is roughly where Polaris is, that's latitude degrees up above your north point. You'll see me work out that math in that other video if you're interested. So we're lucky in the north. We have Merak and Dubhe. They're the front 2 Dipper stars of the Big Dipper, which is also called, and more correctly called, Ursa Major for astronomy. But Merak and Dubhe form a pointer that points to the North Star. And then the North Star is the end of the handle of the Little Dipper. So that should help you be able to find it. And if anybody's going to, Miami or further south, like Australia or something cool, y'all can find the Southern Cross, or you can, listen to a song. I think that was by, Was it Fleetwood Mac? I can't remember who did that. Anyways, the Southern Cross is a cool song. Now, our motion, we can't really perceive that well, not on Earth. But one thing you got to keep in mind is there's always motion relative to what? So, for instance, we think we are sitting still and that the Earth is sitting still because it feels that way. But in fact, we're moving. We're actually rotating about the rotational axis of the Earth. And if you're actually on the North Pole, you're just rotating. But if you go south of the North Pole or north of the South Pole, then you're actually going in a circle as well, not just rotating. So if you keep that in mind, what you realize is, wow, since the distance from the axis is highest on the equator, the fastest speed occurs when we're at 0 degrees latitude. If we go up, say 20 degrees or down 20 degrees, we'll get a lower speed. In fact, it's 1,573 kilometers per hour at 20 degrees. It's 1,280 at 40 degrees north or south. And it's 835 at 60 degrees and north or south, and 290 at 80 degrees. So the neat thing is, if I were to fire a cannon that I wanted to try to shoot due south, I would aim it due south, but guess what's happening? The Earth is rotating under it in such a way that this part is going faster than this part, and that's going faster than this part. So it will appear as if this thing has actually shot off to the right by mistake. If you shoot one from near the South Pole due north, it'll in fact deflect to the left. That's called the Coriolis effect. They call it the Coriolis Force often, but it's not technically a force. It really is the Earth moving under us. So the rule is anything in the northern hemisphere is going to be deflected to the right. Anything in the southern hemisphere is going to be deflected to the left. So even if you're going this way like this, you're still going to feel a leftward deflection. Or if you're going this way like this, you're still going to feel a rightward deflection. That's actually why hurricanes rotate the way they do in the northern hemisphere, and they call them anticyclones in the southern hemisphere because they go in the opposite direction. Pretty cool, huh? The toilets, by the way, we have not seen that toilets go the opposite way, and it shouldn't based on the math, because the mass of the water that you're dealing with is so insignificant that the friction forces of the toilet bowl or the sink or the bathtub are more prevalent than the Coriolis force on such a small body of water. So that's a common misconception. People think the toilets go backwards. Even the Simpsons made an episode about that, and they got it wrong, which is sad because the Simpsons get most of their math and science right.
So if you had an object perfectly above or below the Earth's axis of rotation, it wouldn't be moving 0 kilometers an hour?
Yeah, it would be rotating a certain, basically 360 degrees per almost 24 hours, but it just rotate, not revolve.
Gotcha.
Yep, good point. So that's the Coriolis effect. We don't have to do much with it, but it does help us understand, for instance, like I said, how hurricanes form. I'll give you a quick drawing on that. Let me stop sharing my screen just a second. So we'll go back to this. I'm conserving paper here, so and you'll keep this in case anybody missed it earlier. I'll keep it on the view. So if you imagine what a hurricane is, it's a low pressure zone. Low pressure is where air, wind, all that stuff flies to. So everything goes from high pressure to low pressure. For instance, if you use hairspray or spray on deodorant, the contents in that can's under pressure, so it's a high pressure. And as soon as you open the valve, it sprays out because it wants to go from high pressure to low pressure. So air basically wants to go this way to this low. Does that make sense to everyone? Probably this blue is not very good. It looks like it doesn't show up too well. Okay, so it wants to go that way. But according to the Coriolis force, it's going to be forced to go to the right. And this one will be forced to go to the right. And this one will be forced to go to the right. And this one will be forced to go to the right. And this one will be forced to go to the right. And this will be forced to go to the right. This will be forced to go to the right. This will be forced to go to the right. And I think what you see is ultimately you get a rotation counterclockwise, because all the wind's doing that. Plus there's friction effects, and basically, so that makes it spiral inward as well. But basically, at the end of the day, low pressure zones in the northern hemisphere are going to cause counterclockwise rotations, just like the stars rotating around Polaris in the night sky. So I'll stop this, that and go back to share screen. So now you know why the actual celestial sphere, or why the actual hurricanes go the way they do. Let me see if I can get this thing to go. The sun actually goes through a set of constellations. There's actually 13 of them, but they basically use the zodiacal constellations, which doesn't include Ophiuchus. So this is a picture of it, and this is what Anthony was asking about. This picture is really, really awesome. It helps you do some really cool things, but you got to know how to use it. So I'm going to try to keep my mouse active enough to point out what I can do, because I don't have a ability to write on the screen in this view. So what really goes on, we all know that the sun is sort of at the center of our solar system, and the earth revolves around it. Notice I'm using the word revolve. Rotate is something you do about your axis, and revolve is something you do around another body. So the earth revolves around the sun, and according to this diagram, in the month of September, the sun appears to be in the constellation Leo. That means if I look over here at the sun, I see Leo behind it. If I come to October, then clearly the sun appears to be in Virgo. If I look in November, the sun appears to be in Scorpius. Now what that means is basically about half of these constellations you can't see in November, because the sun is in Scorpius, and you can't see that half of the sky, because that half of the sky is daytime. So Aquarius, you might be able to catch right at sunset or sunrise. I haven't worked out the details of which one it is yet, but same thing with Leo. But you're definitely not going to see Virgo, Libra, Scorpius, Sagittarius, Capricornus in the month of November. So that's part of the thing this diagram can give you. Another thing it can do is it can teach you what time or what constellation will come up, say at sunrise and sunset for any given date. But you got to remember one thing: the distance to these stars is huge compared to this distance. So what you do is you figure out what constellation you're dealing with by thinking about where the Earth is, and then when you go to make a prediction, you put the Earth back here and use that. So let me explain that. With the sun right here, let's take the month of September. The half of the Earth that's facing the sun is experiencing daylight. The other half is experiencing nighttime. The revolution of the Earth is this way, and the rotation is that way. So the Earth is rotating that way. That means I go from noon to nightfall right here. So I'm on this side of the Earth, this back edge of the Earth at nightfall. If I wanted to know what constellation is directly overhead at sunset or nightfall, I'd say, okay, well, I need this angle right here, which seems to be parallel to this line, but I need it as if I were here because this distance is so insignificant. So I'd say Scorpius. See how I did that? I shifted the Earth. I found what angle I'm talking about, which is right here, and I shifted the Earth to the center, and I say, oh, that's Scorpius. So Scorpius is the constellation that's directly overhead at sunset in September. If you wanted to do sunrise, you'd say, okay, well, again, the middle of the Earth facing, on the side facing the sun is noon. A quarter of the way around is sunset. Another quarter is midnight. Another quarter, which would be this front edge here, is sunrise. So I'd say, okay, I need that same angle again, which is parallel to this line right there. So with that in mind, now I'll put the Earth over here and look along that line, and I say, oh, Taurus. So in September, I would expect Taurus to rise at sunset. I mean, at sunrise. Or excuse me, Taurus to be directly overhead at sunrise. Sorry about that. If I wanted to know what would be directly overhead at midnight, I would want myself to be on the opposite side of the Earth from the sun. So that would be over here on the back side. And this one, it doesn't really matter if I move the Earth or not. In both cases, I get Aquarius is directly overhead at midnight in September. So this will be, all this video is going to be recorded anyways, so y'all should be fine if you need to come back and look at that. But that's how this diagram is used. If I wanted to do November, I could do the same thing. Remember, let me show you from above what that's supposed to look like. I'm going to stop sharing just a second. I got Taurus on this side, I got November here, I got the sun, and I got Scorpius. So I'm going to stop sharing and show you the screen again. Okay, let's make a good use of our paper. I'm going to use an entirely different color so we can ignore the blue. So what we're seeing in that diagram is the sun, Taurus, and if I remember correctly, it was also Scorpius on the other side. Let me double check. Yeah, Scorpius on the other side. So I go back here. Scorpius is on the other side. And the Earth is right here. So the key thing to remember with this is the Earth is orbiting this way, and therefore it's also rotating this way. And the half of the Earth that faces the sun is experiencing daylight, so all these people are nighttime. So as the Earth rotates, if you were right here, do you see what time of day you'd be experiencing? Let me focus that a little better too. What time of day would you be experiencing at this location on Earth? Anybody know?
Midnight.
Midnight, because the sun's like below your feet, right?
Mm-hmm.
And right here, it seems to be directly overhead, so that'd be noon. Now, the Earth rotates this way, so as you rotate with the Earth, you go from nighttime to daytime right here, so that's called sunrise. Which, for most of our models, we pretend that's roughly 6 a.m. So this is midnight right there. That's noon right there. So if I ask you, hey, what constellation is directly overhead at midnight in the month of November, you'd say, oh, it's directly over my head right here, so that's Taurus. But that's one of the easy ones because you don't have to remember the angles and stuff like that. If I ask you what constellation is directly overhead at sunrise, then I'd want to look for the constellation that's this direction, but from this location. So I go back to my diagram. Everybody see that, what I'm looking for? I'm looking for basically the line perpendicular to this one. So this line is the line connecting the sun, the Earth, and the month of November. And I want to go perpendicular to that and ahead of the Earth. So now I'm going to go back to share screen. And this is what we find at sunrise, what's directly overhead at sunrise in November. And
Maybe Virgo.
yes, exactly. It would be, well, wait a second.
No, Leo.
Yeah, exactly. It looks like Virgo because of the way I drew it versus the way it is. But yeah, if you go 90 degrees, it would be this one, so it's Leo. Did everybody see why she thought Virgo? I had drawn my stuff like this, like the Earth was right here and the sun was right here. If you go perpendicular to that, you'd be over there. But no, you want the line that we were doing, which was this one, and you go perpendicular to that, you say, oh, Leo. So Leo's directly overhead at sunrise in November. Does that make sense?
Just look at every 90 degrees you can change.
Yeah, the 90 degrees is pretty much a key indicator on this. You'll see later when I do another video on the moon diagram. There's a cool moon diagram. It's actually in these slides that allows you to predict what time the moon rises and sets and crosses your meridian, all sorts of cool stuff. Okay. All right. So
I'll explain it a lot better because I was kind of confused when I was doing the homework for it.
Right.
I wasn't understanding what was going on.
Yeah, it's weird. They can tell you everything, and you've got enough to put all this together. But until somebody explains how to use it, it's often very hard to figure out. It took me years to figure out how to use that diagram. And that was, when I was an undergraduate and graduate student teaching it. So it was really, really difficult. But now that I understand it, I can explain it to other people. So yeah, that's perfectly normal. Maybe Einstein would have came into the class and figured it out right off the bat, but most of those other people are normal. All right, let me show you the next slide, see if there's, okay, so this is, and I mentioned that in the other video, this is actually the quote-unquote reason for the seasons. Because of the Earth's axial tilt, it's tilted 23.5 degrees. That's why the ecliptic's tilted at 23.5 degrees. You see that the sun's rays here are almost directly vertical, well, they're directly vertical on the Tropic of Capricorn, for starters. But as you get further and further down here, they're still closer to vertical than when you get further and further up here, vertical compared to the Earth, that is, to the Earth's surface. So the light is much more intense on the southern hemisphere here. When you get over to this side, the light is more closer to vertical in the northern hemisphere, and therefore we get summer in the northern hemisphere during this part of the orbit. Does that make sense? Falls would occur, fall and autumn, or excuse me, autumn and spring would occur at the midpoint between the two. So if you look at it, if in the winter, the sun actually is low in the sky, and a 1 meter by 1 meter window of sunlight would have to cover a 2.24 by 1 meter block. Whereas in the summer, if it was this angled high, then it's only tilted by 16.5 from the vertical. And you don't need to know how they got those numbers. I can show it to you, but it's not that relevant. The main thing is in the summer, you realize this angle from vertical is very small in the summer. Whether you're northern hemisphere or southern hemisphere, when you're having summer, that angle's small. And when you're having winter, that angle's big. And because of that small angle, this 1 meter by 1 meter window only has to spread the light over 1.04 meters by 1 meter. So you can see it's more light per square area just because the area got smaller in this case than it was there. So one of the reasons for the seasons is that the sunlight is spread over a smaller area, and therefore it's more intense. That's the definition of intense. It's the amount divided by the area. That's an intensity measurement. So the sunlight's more intense. You also find out, though, because of the sun's location apparently on the celestial sphere, the sun is actually up a lot longer during the summer than it is during the winter. Because the sun, for us, in our summer, the sun is in the northern part of the celestial sphere. In fact, it's at positive 23.5 degrees on 621. So the sun has to rise a little less than 23.5 degrees north of east, and then go all the way to the south, and then rise or set a little less than 23.5 degrees north of west. So that path going around the Earth is a lot longer, and therefore the days are longer. Let me see. I think they had a diagram on that. You can see the solstices stacking up there. No, they didn't do it in here. I could have sworn they had it. All right. That's basically what I'm going to cover. Let me do one more quick drawing because my art is looking so horrible today. Let me do one more quick drawing to show you what I mean about the length of the day. I want to stop sharing again and go back to my screen. So if you look at the horizon for a given person, it's actually an oval, right? And this would be, say, their north point. And this would be their south point. Okay. This would be their east point. Yes. And this would be their west point. That don't feel right. If I'm looking north, yeah, I guess that's right. Okay. So the equator, the way it works, the celestial equator always hits our horizon due east and due west. So it's going to come up like this if this is our dome of the sky, if you will. So that's like our part of the celestial sphere. It's going to go up like this and then come down like that. That's the celestial equator. Now we learned from this drawing I showed you earlier that, look right here, on 621, that's the summer solstice. Notice the sun is 23.5 degrees above the celestial equator, because 0 degrees declination is actually the celestial equator. So this celestial equator, by the way, which if you look at the other video, you already know, it is 90 degrees minus L up from the south point. So for you guys, it's like 36 degrees. So I'll say roughly 90 degrees minus 36 degrees. 90 minus 30 is 60, minus 6 is 54. So that's roughly 54 degrees high is how high the celestial equator is. But here's the kicker. On the summer solstice, the sun is an additional 23.5 degrees higher than that. So that means its path is like that. So the sun is actually going to rise not quite. You know, if I measured it perpendicular to this line, that would be 23.5 degrees. So clearly this is not 23.5 degrees, but the sun is definitely going to rise north of east, go all this long path, and then set north of west. That's on 621 and approximately 621. Okay. Now on 320, or excuse me, on 1221, it will actually be 23.5 degrees below that. So it would actually rise here, follow this line, and then set here. So you can see that path is very, very short for 1221. So that's another reason. Not only is the light less intense during the winter, the sun's only up a very short amount of time in the winter. Does that make any sense to you guys? All right, so I hope that helps. Anyways, try to make out some of the stuff that we were talking about. This diagram is extremely important because I can ask you questions like, once you realize the formula for the angle from the North Point up to Polaris is latitude degrees up. So if you're at 35 degrees latitude, you expect to see Polaris 35 degrees above your horizon. So if you go out in the ocean, for instance, and you use a protractor to sight due north of you, the horizon, and then you look up to Polaris and use that protractor to measure that angle, you'd get that would be roughly 36 degrees if you're off the coast of Virginia Beach. Not only that, 90 minus your latitude is the angle from the South Point up that the celestial equator is. So now I can ask you, how high is the sun on 621 if you live in Virginia Beach? You say, well, the celestial equator is at 54 degrees. On 621, the sun has to be another 23.5 degrees. So 54 plus 23.5 is 74.5 degrees. So we know that in Virginia Beach, the sun will be 74.5 degrees above the horizon at noon. That's the highest it'll get. But that's pretty high. It's not quite 90, you know, like it would be if we were at the equator or between the tropics. But it is pretty high. And then if I ask you how high is the sun on 1221 in Virginia Beach, you'd say, well, I know the celestial equator is at 54 degrees. So now I'm going to subtract 23.5. Well, 50 minus 20 is 30. Minus 54 minus 23 is 20. Wait a second. 53. Yeah, 54 minus 23 would be 40 minus 3. That'd be 30. Or excuse me, 30 minus 3. That'd be 27 degrees. Minus a half. That's 26.5 degrees. So the sun's only going to reach 26.5 degrees high during the day on 1221 in Virginia Beach. So those are questions that'll happen as well. You can get the formulas or figure out how those formulas came to be. There's something you need to memorize for tests. Actually, since our tests are online, you can probably write them down. Just as long as you know how to use them, it'll be fine. If we get to have a face-to-face final exam, a proctored final exam, which I doubt we will, if we get to do that, then you'll have to have it memorized. Otherwise, you'll still have your cheat sheet stuff. You'll be allowed to have your notes and all that good stuff. Okay. Any questions on that, you guys? And ladies and women and girls and dudes and dudettes?
Nope.
Nope. Anybody have any questions about anything in general? Excuse me. Don't know why I did that. Stop share. I went to go to the video and hit the wrong button.
So the tests are cumulative?
Yeah, every test is going to cover material from the previous chapters as well.
Okay.
The first test obviously is not, but all the other ones have to be.
If we have a question like that where you ask us on this date, what is the degrees or whatever, will that chart be in front of us for that question?
No, that's why you got to sort of work that out from, and that's why I gave it to you both in that video and again today, as I wanted you to see it. It's pretty easy to memorize. You should be able to picture that at an instant, as well as those ideas about how the stars move in the night sky, the ones where I drew the circles and all that good stuff to show you that. I tell my students to just, let me do a share screen again, or let me do a different video again. I tell my students in general to make sure they memorize this diagram and memorize this diagram. And then, of course, also memorize that diagram. That's just something. And if you draw it a couple times or even work it out yourself instead of memorizing it, if you actually figure out why it is what it is from these diagrams that you see in your book, it takes nothing. You're not even memorizing it. It's just like you're understanding it, so it's completely obvious. Okay. I can ask you also with that, I can ask you more complicated questions. So I could ask you about 625, even though that's clearly not one of the key points on here, but I will have multiple choice and one of them will be the best answer, even though a couple of them might look like good answers, but one will be the best. And it doesn't require really any math. It requires you to understand, like students will often think at 621, it reaches 23 and a half. So at 623 or 625, it's going to be even higher. Well, that's sort of misunderstanding the diagram, right? So I'll have choices like 23 degrees, but I also have choices like 24 degrees for declination. So stuff like that comes up. But yeah, I definitely get them to memorize that. And these guys, and there's also, I talked about it in the other video, there's another thing that you got to keep in mind, the sidereal day versus a solar day. Have y'all run into that wording yet in any of your assignments? It's kind of weird, but the sidereal day is what we call a day with respect to the stars. It's basically how long does it take for the Earth to make a complete 360-degree rotation. If you look right here, here's the Earth, and we've got a vertical pole. Let's say it's 321, and we've got this vertical pole sitting on the equator. Then the sun's going to cast no shadow from that pole because it's directly overhead, right? So if we just rotated where we were at, a 360-degree rotation would give me again that same noon time of the day where the shadow casts no pole. I mean, the pole casts no shadow, right? But that's not what's going on with the Earth. The Earth is rotating, but it's also revolving. So if I do this and go all the way over to here, such that I get a 360-degree rotation, I see now the sun is not going to not cast a shadow there. In fact, the sun is going to cast a shadow this way here. So that's not noon. Noon is when you go from you go from casting no shadow to casting no shadow again. So in fact, I've got to go a little bit further along until this pole points back towards the Earth. So this is the whole day. This is called a solar day, and that's a day with respect to the sun, which we call solstice. That's why we call it a solar day. You can work out the math, but basically, if you realize that there's 365.25 days in a year, and it goes through a 360-degree rotation, you get 0.986 degrees per day. So you know that's how far it has to turn here. So the sun actually has to turn an additional 0.986 degrees beyond 360 to get a solar day, whereas the sidereal day is 23 hours, 56 minutes. So that brings in another question that we can ask with these. A 360-degree rotation brings distant stars to the exact same spot in the sky, and that takes 23 hours, 56 minutes. Whereas a solar day is 24 hours, and that turns us 360.981 degrees. So let me show you what that means. If I said a star was due east of us at 8 p.m., and then I asked where would it be at 8 p.m. the next night, you would still have these same choices. Can anybody think where the star will have moved at 8 p.m. the next night?
Not at all.
That's if a solar day was equal to a sidereal day, and that's the common answer that students give. It actually is, remember, 360 degrees. Basically, this star is going to go like this, make a complete circle, come back around. When it gets to 360, the star will be there, but that's going to be at 7:56 p.m. because a sidereal day is 23 hours and 56 minutes. If you wait till 8 p.m., it's going to have moved basically 4 minutes further. So it will have moved the same way as if it was 8 to 9 p.m., only a lot smaller.
Mm-hmm.
So the answer is, again, up and to the right. So if I go 8 p.m. from one day to the 8 p.m. the next day, the answer is up and to the right for east. It's down and to the right for west. It's down and to the right for south. It's up and to the left for to the right of Polaris, and all those same answers. But if I see a star at 8 p.m. one night and come back at 7:56 the next night, then the answer will be
Not at all.
not at all. Exactly. So that's another set of 7 questions that I can ask you.
So when it comes to stars in the sky, once it goes around one solar day, the stars move very slightly.
They all move at the same rate, more or less. But yeah, what you're seeing is it's going to move a little bit further to get to from a solar day to a sidereal day. It's only going to be 4 minutes of rotation later.
Okay.
Does that make sense?
Yeah.
See you, Tristan. I think Roshana has got now understands the question I was talking about. Celestial sphere is to Earth as the blank is to blank. So that's just analogies. They should all only have one blank line out of the 4 possible choices. So you just look at the analogies between longitude and latitude and right ascension and declination, and Earth versus celestial sphere. The north celestial pole is to the celestial equator as blank is to the Earth. Y'all can probably figure out that would be North Pole. Okay. Anybody have any other questions? That's a lot of material. Go back and watch that video. I explained this stuff a lot better. I just was sort of bringing you up to speed because I know you hadn't seen it yet. And my next video will probably be on moon phases. And that one's got an intense model, not unlike this one, where I pictured how the celestial sphere was moving. And that allows you to answer cool questions like, a guy's driving at night and he looks out his driver's side window and sees a fingernail clipping shaped moon. What direction was he driving? If it was low in the sky, what time of night was it? All sorts of cool questions like that. So I am going to go ahead and open up your practice test as well as your first test. I've now made that first test due a week from today instead of Monday. So don't worry about that deadline. Make sure y'all all get a chance to take the practice test a bunch. If anybody has been in my class before, they will tell you the practice test is the way you succeed on Mr. Younger's test, because I use the same bank of questions for the practice test as I do for the actual test. The only thing is I reserve the right to change about 10% of the points to new questions that I just made up.
So if I take a practice test and get a good grade, then I can assume that I'll get that's a similar grade on the actual test?
Well, it's a little more complicated because you get 10 questions at a time and there's like 150 questions in the bank. So if you took it an infinite number of times and you averaged an 80, I would say there's a high probability you're going to get at least an 80, but maybe even 100.
Okay.
Does that make sense?
Yeah.
Because each time you take it, it's slightly different, but it's only 7 minutes. That's why I made it 10 questions long, because I wanted you guys to be able to take it a lot.
Okay.
Okay. Caitlin, do you have anything, hon? I'm sorry for the hun. I do that. It's a Southern thing. I'm not a jerk. Like
You're fine. No, I'm good. Thank you.
Okay. Haley, you good? How about you, sweetie, Anthony? You might not even be there anymore. Anyways, you folks have a good one. Stay safe. Don't get sick. I will speak to y'all next time. Like I said, I'm still working on possibly having a second meeting, so just pay attention to your emails, and I'll announce if I'm going to do something like that. Thanks for hanging around. I hope this helped.
Thank you.
Thank you.
Thank you.
You're welcome. Have a good day. Bye-bye.
You too.
You too.
Bye.